brings us to a new topic, which is going to matter as we talk about explosions and more complex momentum conservation. So this is going to be the center of mass, okay? So here's a quick question, just intuitively about the center of mass. Assuming these two things have the same density, they're made of the same material, where's the center of mass? Okay, yes, so we all kind of have an idea of what center of mass looks like. If this thing is more massive than this thing, that means that the center of mass is going to be closer to the larger amount of mass, okay? So that's going to be A in this case. But let's try another one. It's always the best answer with, okay, we've changed nobody's mind. But D is the second best answer because there could be some weird crap going on where like this thing isn't uniform, but let's just say everything is made of the same material, of the same color. So in that case, the answer is going to be A. And there's sort of an intuition to this, right? You know that you've probably experienced something like this before, but if this thing were in the middle, you would assume they were about the same mass, but because it's closer to this, it's probably heavier, okay? Later we'll talk about torque, but we're not there yet. So let's talk about the definition of the center of mass. So this is the point about which an object will freely rotate. So for instance, and it's directional. Let's see if this is a good idea. Yeah, okay. So it's like the center on this thing because it's fairly uniform. If you have an axe, where is it going to rotate?
Just below where the head is.
Yeah, just below the head because most of the mass for an axe is going to be in the head, okay? So it's also the point at which an object would balance like a seesaw, and that is actually directional, right? So like there's a center of mass along this direction. There's a fun trick you can do where you just slide your fingers together, and where they meet, it's hard to get the last part, is where it should balance. We can talk about why this works when we talk about torque, but essentially it has to do with the fact that friction is related to normal force, right? So as I move my fingers, once it gets in balance to the normal force on the opposite side gets bigger because it tilts that way, and then that creates more friction, and then the other one moves. And so it's kind of a fun physics experiment, but you can always find the center that way. If you turned it this way, you'd be able to find the center this way. It's harder to balance on this axis, right? Like this way, and it's also harder to balance here, okay? But it's directionally dependent. So if you have a three-dimensional object, it has three center of mass points of balance. They usually coincide in the same place, but you have to figure it out in X, Y, and Z. So, the way you calculate center of mass, if you just have objects, in this case, the center of mass would be here, so you would call this point the center of mass. You want to set up a coordinate system, so it doesn't really matter how you do this. You could call this 0, and then this distance would be x1, this distance would be x2, and this would be the distance to the center of mass, okay? You always choose your 0. You just have to be consistent. If you call this 0, then you just have a negative value to x1. It just changes the way that you do the coordinate system, but it doesn't change the answer. It should always be in the same location with reference to your 0, okay? The way you add these things up, you sum up in the X, Y, and Z direction, but what you're saying is basically you start from 0, and it would be mass 1 times the distance of that mass from 0, okay? And then mass 2 times the distance of that mass from 0, and then if this object actually has mass, okay, then it would be the mass of this times the distance of its center of mass from 0, okay? It's easier when these things are points. If they're full objects, you have to measure to their center of mass. So individually, objects can create one large object, okay? You do this for x and y, and then you divide it by the total mass. So in this case, it would be x1 m1 plus x2 m2 plus x center of mass times the mass of this thing, so mass of whatever this plank is, divided by m1 plus m2 plus the mass of this thing. And that would give you the center of mass, okay? So these are the equations, and you're really just summing up masses and distances and dividing by the total mass. And that will always give you your center of mass, okay? So we'll try out a problem. So let's say we have, if we have a meter stick like this, we want to calculate the center of mass for the whole system, okay? So let's say that we know the meter stick has is 90 grams, and we hang a mass at the 20 centimeter mark and then another one at the 80 centimeter mark, but they're different size masses. So I'm going to draw this out and we're going to do this together to calculate the center of mass. Okay. So let's draw a meter stick. Hey, that almost worked. It doesn't, I'm so bad at drawing straight lines that this thing is like taunting me. Cool. Oh, that's good. Okay, so let's say this is our meter stick. This is, we're gonna call 0, 0. So are we okay with that? Okay, so this will be 0. This is 100. There's, let's see, 20, say this is 50, 30, 40, 50, 60, 70, 80, 90. It's not perfectly drawn, but you get the idea. So we have a mass at the 20, so this would be 100 grams. At the center of mass of the meter stick, we know this is 90 grams for the meter stick, and then at 80 centimeters, we've also hung a 200 gram mass, okay? And just for space, I'll bring this down. So, what are our distances? So we'll call this, let's call this M1, M2, and mass of the center of mass, okay? So we have, this would be X1, right? This is gonna be X of your center of mass. And then last but not least, we'll have X2, which is 80 centimeters. This is 20 centimeters, and this is 50 centimeters, okay? So when we add up our X center of mass, what we want to do is 1 over the mass total, the sum of all the X and M's, okay? So that's going to be, just in symbolically, X1 M1 plus X2 M2 plus X center of mass times the mass of the meter stick, divided by M1 plus M2 plus mass of the meter stick. So that's going to look like, and this is all in centimeters. Are we going to need that? Do we need to convert? Looking at how the units cancel, it's mass times distance divided by mass. So do we need to convert the mass? Can we leave it all in grams and centimeters? As long as they're all in grams and centimeters, it should cancel, we should get the right thing, okay? If you're not sure, convert, but in this case, the units cancel. If we start with centimeters, we should end with centimeters, so that should be fine. So I'm not going to change these, so that's gonna be 20 centimeters times 100 grams plus 80 centimeters times 200 grams plus 50 centimeters times 90 grams divided by the total mass, which is 100 plus 200 plus 90, so 390 grams. Okay, if you plug all that in, that should give you something at 57.7 centimeters. So the center of mass of the whole system should be somewhere right here. Okay, does that make physical sense to you guys? Yeah, okay. There's another way to do this. If you wanted to measure from the middle, okay, let's say you called 50 0. You could get the same answer. Let me just sort of write it out. It would look like, instead of this, you would end up with this first distance would be -30. So you'd say -30 times 100, right? So -30 centimeters times 100 grams plus 30 centimeters times 200 grams. And there would be no, then you just have plus 0 there because this would be 0, so the position would be 0. And then you divide that by 390 grams, and that will not give you 57.7. What will it give you if you called this 0? It still has to end up here. So if this is 0, how far is this distance? Yeah, it should be 7.7. So if you change the 0 to the middle, this will give you 7.7 centimeters, which is the same position on the meter stick with reference to what you've called 0. So it doesn't matter where you pick the 0. All that matters is you do all your measurements from that point. Okay? Just a little side note. The other thing that we're sort of assuming that isn't necessarily intuitive is that for the meter stick, you treat its mass as acting at its center of mass, which is like a little bit meta considering where we're at in learning about center of mass, but we'll get into the details of why that is as we move forward. For now, just anytime you have an object that's not a point, you treat all of most of your forces like weight and a lot of your action as happening at the center of mass, okay? And there's actually, like, if you want to think about that, that makes sense. So, for instance, if I throw this, if this were a dot and I throw it, what's the shape of the motion? Parabola, right? If I just throw this thing, like if I just throw like a golf ball, right? It's a parabola. If I spin this thing and throw it, right? The total motion of the center of mass is still a parabola, but there's all this extra motion from the rotation. So what I mean is, like, if you wanted to predict how this thing was moving, you'd need to be able to predict the spin, but the center of mass would still follow the rules of kinematics that we've already defined. Okay, so that's one of the useful things about center of mass. It's two different.
Okay, so we've talked about how we can find the center of mass of a bunch of objects, but what if we just want to find the center of mass of one object? Well, what we do is we break the object into little tiny pieces. And then, because there's so many little tiny pieces, if we want it to be a continuous object, we can make each little tiny piece infinitesimally small, and we can sum them all up. But if you make the pieces really small, now this becomes an integral. The tricky thing here is dm. This is the derivative, like sort of not the derivative, but it's the infinitesimally small piece of mass. So one of these little guys, okay? The thing about this is it has to be rewritten in terms of x, and this would have to be rewritten in terms of y. And so here we're going to use something we might remember from previous parts of the class called density. So remember, you can only integrate over coordinates, so integrating over dm doesn't work, so we have to convert dm to dx or dy or dz or dr or d theta or whatever coordinate system we're using, and then move forward from there. So this is our full definition of our center of mass for any object. And I'm going to show you how we can use this to actually calculate. Okay, so let's figure out how we get the center of mass of a thin uniform rod of length L. So let's draw this out. So first we have to have our rod. So this is a thin uniform rod of length L, and we'll fill it in. Okay, so this thing has a length L. We want to draw our coordinate system. So let's say we have an XY coordinate system. So that would be Y, but we don't really need that. We just need X. okay? So we're gonna call this 0, and then this will be L. So 0 to L. Let's move the 0 over. So 0 to L. Well, our definition of the center of mass is X center of mass is equal to 1 over M, the mass total, right? And we already know the mass total is M, of X dm. So let's talk about what dm means, okay? So in this case, dm is like a little chunk of this guy right here. But that means dm has a length we'll call dx, okay? And the reality is if you split this thing into a bunch of little pieces, there's just a bunch of little dm's here, and it's broken up into lots of little chunks that are all of size dm, okay? But the key here is that dm has to turn into dx. So how do we figure out how much mass is in this little thing? Because all we really know is that we have this big mass, m, and we have a length L. So let's go to something we call linear density. And linear density is just like density, but instead of mass over volume, it's just mass over length. So we'll call the linear density mass over the total length, okay? So this is our density, which means that if we know how long something is, we can multiply it by density, because remember, density is mass over length. So if we want to figure out the actual mass of something, then our mass, any mass, like dm, is going to be lambda dx. So the density times the length, right? So that gives us dm. So since we know that lambda is m over L in this case, because we have a uniform density, right? Uniform rod means uniform density. We end up with m over L dx. That's our dm. So when we write this in, we have 1 over m, and x, we replace dm with m over L dx, where m over L we know to be constant, so we can pull those out, okay? The other thing we know is we're integrating this from 0, right? We're integrating the whole rod, so we integrate from 0 all the way to L, right? So we're adding up this piece, so the length to this piece and its mass, then the length to this piece and its mass, then the length to this piece and its mass, then the length to this piece and its mass. The x represents this length, and this represents the mass, okay? So we cancel this, you end up with 1 over L from 0 to L x dx. All right, so let's plug this in. We have 1 over L, 1/2 x squared from 0 to L. So that gives us 1 over L times 1/2 L squared minus 0, right? Squared. So we get 1 over L squared times 1/2. Get rid of one of those, and you get L over 2. So your center of mass is at the halfway point, which we should have guessed. Since this is a uniform rod, remember a uniform rod like this is going to have a center of mass at the center. Now we have derived that. So just thinking about collisions and what center of mass means, explosions are sort of reverse inelastic collisions, because remember, an inelastic collision is objects colliding and then sticking together. An explosion is now one object that splits into multiple objects. So we can think about this in terms of recoil, and using these values, we can figure out what the force and acceleration of things should be. So for many particles, right, we can just add up all of the momentums, and they should all add up to 0. So for instance, if it's an explosion, the initial momentum's probably something like 0, and then each of the pieces is going to have momentums that add up to